Good day everyone. We are Group 1 and we are here to present the solid waste management of the mining industry. Firstly, to understand the significance of the waste mining industry, the mining industry generates significant amount of solid waste from leftover rocks, including mine tailings, overburden, and processing residues. These waste can have significant environmental impact if not managed properly. Continuing on the waste analysis and characterization survey, most of the avenue of the waste comes from these five processes or location of processes. There are overburden and waste rocks, which is basically soil and rock removed during mining to access ore deposits. These are commonly non-toxic, and to properly manage this, effective management strategies that include storing or using it in infrastructure developments are used. Next is tailing. These are the waste materials left after extraction of the valuable materials from ore. These, and these are commonly toxic. Next is the chemical waste. These are chemical used in ore processing which can be sometimes be solid. This is also commonly toxic. And next is general use. These are waste from daily operations such as plastics, metals, and papers from everyday use on the office activities. And lastly, recyclable waste. Materials that can be processed and reused, which can be scraps, metal, or plastic. To further understand the waste analysis and characterization surveys, each of its contribution to the waste is graph. Firstly, the overburden and waste rocks, which is 80% of the waste produced of the solid waste produced in the mining industry. Next is tailing, which is about 14%. Next is next is the recyclable waste, which is 3%. Next is chemical waste, 2%, and lastly, general use, which is about 1% or less than 1%.
Mining operations generate significant waste with overburden and waste rock, along with tailings being the top contributors. Overburden and waste rock make up the largest portion of mining waste by volume, while tailings, though smaller in quantity, pose a greater environmental risk due to their toxicity. These two sources highlight the critical need for effective waste management strategies to address the environmental and operational challenges they create in mining. Mining operations begin with the removal of overburden and waste rock, which is the top layer of soil and rock that must be excavated to access valuable ore deposits beneath. These materials make up the largest portion, as my groupmate said, of mining waste, accounting for 80 to 85% of the total. Overburden and waste rock primarily consist of natural materials like silica, clay, aluminum, and iron. While generally non toxic, the sheer volume of this waste is what makes it significant. Think about it. For every ton of ore extracted, several tons of overburden are removed. Without proper management, this can overwhelm storage capacities and even disrupt ecosystems. Interestingly, overburden and waste rock are not entirely useless. With effective strategies, they can be repurposed in construction or infrastructure projects. However, the scale of removal and storage remains one of the top challenges in mining operations. Overburden and waste rock are a top concern in mining for two main reasons: their sheer volume and their environmental impact. First, their sheer volume is staggering, constituting the vast majority of mining waste. Mining sites generate hundreds of millions of tons of this material annually, creating immense logistical and environmental challenges in handling and storage. Second, while overburden and waste rock are often non toxic, they can still cause significant environmental issues. When exposed to air and water, certain minerals may oxidize, leading to acid mine drainage, a phenomenon that can contaminate surrounding soil and water systems. The management of overburden and waste rock must be efficient, as any failure to handle this massive waste stream responsibly can lead to irreversible damage to local ecosystems and communities. Moving on to tailings. Unlike overburden and waste rock, tailings are the leftover materials from the ore processing phase. After the valuable minerals are extracted, what remains are very, very fine particles mixed with water and residual chemicals. These account for 10 to 15% of mining waste, which may seem small compared to overburden and waste rock, but tailings carry a much higher environmental risk. Tailings often contain toxic substances like heavy metals and chemicals from the mineral extraction process, making them a key contributor to environmental pollution if not managed carefully. Their fine grained nature also makes them prone to erosion, and when improperly stored, they can contaminate nearby soil and water systems. Tailings might represent a smaller volume of mining waste, but their risk profile makes them one of the most critical issues in the industry. The primary concern lies in their toxicity. Heavy metals, along with the chemical reagents used during ore processing, often remain in tailings, which can leach into groundwater or surface water if containment systems fail. Additionally, the fine slurry like consistency of tailings makes storage a challenge. Tailings ponds are often used, but they require constant monitoring to prevent leaks or catastrophic failures, such as dam breaches, which can devastate ecosystems and communities downstream. Managing tailings is not just about storage, it's about risk mitigation. Reducing reliance on chemicals, improving tailing storage, and exploring recycling options are essential steps to address this top environmental concern. So there you go. Those are the top two concerns, which are overburden and waste rock and tailings.
So for summary, ito ulit yung schematic diagram natin para sa mismong mining process. So for the entire process no, andito yung in and out ng mass and energy. So sa mismong ore deposit exploitation, um, may kinakonsume dito na water and then energy for transporting ng mga equipments and ores pati yung energy sa mismong excavation. Next yung main ng mga output nun is meron tayong emissions and dito yung air, water, and solid pollution. So may CO2 in dust, air pollution, excavation water, and then exhausted oil. And then yung main product naman dun is yung tufinat or dito yung mga ores na nagpo-proceed sa mineral processing. And then again, here may consume ulit tayo na materials and energy for transport ng reagents and water. Tapos yung reagents and water naman mismo yung mga kinoconsume na mass. And then, after this process, makukuha natin yung concentrate or yung extracted minerals. And then again, meron din tayo dito mga emissions. And then yung pinaka-waste product is yung waste and tailings na either malalandfill or pwede silang undergo treatment or further analysis for better waste management. So ito naman yung schematic diagram para sa mismong solid waste management system. So this will be discussed in depth sa next part wherein isa-isahin yung mga processes. Pero in summary, dito yung process nag-undergo yung ating tailings and waste rock, yung ating primary wastes, wherein pwede silang maging recycle used as soil additive or mag-undergo ng treatment before sila i-dispose o kaya i-prepare sila for sampling for further solid waste analysis para mas better equip tayo kung paano sila i-handle nga for improvement sa ating waste management system.
For the mining industry solid waste management operation, first we have site investigation. So in the investigation, it was performed to collect information about mining history, waste topology, and location. The facility is suitable for characterization and sampling. The location and the number of sampling points are often site-specific, but in general, a systematic sampling strategy is adopted to obtain the representative data of the whole waste facility. So next is sampling. The sampling design in the field is usually planned according to the nature of the primary contamination source. The type of pathway and duration of the contamination determine the sampling design. When sampling was done on sloping ground sites, samples were collected downhill or downwind concerning the source as well as uphill. And for the tailings, its sample size fraction is ranging from 0 to 0.62 millimeters. So first we have drying and oven. So it removes moisture from tailings to ensure consistency during further analysis. Dry tailings are less reactive chemically and physically, making them suitable for further testing. So second is screening and quartering. Screening is dividing the material into uniform size fractions, while quartering is reducing the sample size while maintaining representativeness. Screening helps separate fines from coarse materials, enhancing the precision of recovery experiments and geochemical analysis. Moreover, quartering ensures that the reduced sample retains the same characteristic as the original bulk material. So third is usage as soil additive. So part of the material is evaluated for its potential to be repurposed as a soil additive. Recycling tailings into soil amendments minimizes waste and supports sustainable land use practices. It also reduces the need for disposal for finding alternative uses for the material. And next is recovery experiments. So another fraction is reserved for recovery experiments to test resource recovery methods. This step aims to convert waste into resources since optimizing from tailings reduces reliance on primary mining, minimizing environmental degradation and resource depletion. And for the geochemical analysis, samples are analyzed for their chemical properties to assess the environmental impact and usability. Analytical techniques like X-ray fluorescence and inductively coupled plasma or ICP spectroscopy may be employed. It ensures the material safety and usability for recycling or recovery. So the last one is flotation and shaking table. So it is used to separate the valuable minerals or metals from the waste material. Flotation separates valuable minerals from waste through the use of chemicals and air bubbles. Meanwhile, a shaking table is a gravity separation technique that uses the differences in density to separate materials. With that, tailings can be repurposed as a soil additive, promoting sustainability in agriculture and land rehabilitation. Moreover, extracting additional value from waste reduces the environmental impact of mining operations. Geochemical analysis ensures that any reuse or disposal of tailings is environmentally safe, preventing contamination of soil or water systems. By exploring recycling and recovery pathways, the need for tailing storage facilities is reduced, mitigating the long-term environmental risk.
So now, before we proceed with the treatment, let us first define what are waste rocks and the operating residues. So waste rocks are the largest byproduct of mining, which includes overburdened topsoil and other rocks removed to access ore in complexly shaped deposits in both surface and underground mines. Meanwhile, operating residues are the portions of the crushed, milled, ground, or washed and treated resource deemed to be too poor to be treated further. Now, continuing with the flowchart presented earlier, these waste rocks and operating residues would undergo sieving to be separated into two different fractions, which is the fine fraction and the coarse fraction. So, the fine fractions from the waste rocks, residues, and tailings are then combined and analyzed for suitability as a soil additive and based on their chemical and bioavailable concentration. So, this form of recycling helps minimize the waste by turning it into a more usable form for other purposes. So, in here, we can see that it was used for seed germination or as type of fertilizer. Meanwhile, for the coarse fractions, they are processed with a jaw crusher to reduce their size and then sieved to obtain particles of approximately zero point 0.5 to 1 millimeter. So, doing so ensures uniformity in size, which leads to becoming more manageable to test and control the amount of material used for future recovery process. Meanwhile, recovery experiments aim to convert waste into resources since optimizing from waste rocks or operating procedures reduces the reliance on primary mining, which minimizes the environmental degradation and resource depletion. And some examples of these experiments are the flotation and shaking table as well as the geochemical analysis. So, for the flotation and shaking table, these are methods used to extract valuable minerals or metals from the waste material. Flotation employs chemicals and air bubbles to separate the valuable minerals, while a shaking table uses gravity and density differences to achieve separation. Meanwhile, in geochemical analysis, the coarse fractions are analyzed using techniques like XRF or ICP to assess their chemical properties, and this ensures the safety and suitability for recycling or recovery of the materials.
And now let us have the sustainable suggestions for improving the environmental and operational efficiency of mining treatment plants. Let's start with the resource recovery and the circular economy. First, resource recovery plays a vital role in minimizing waste and creating value from byproducts. In the Philippines, there's significant potential for repurposing tailings in construction. For example, tailings can be used as aggregates to replace sand in concrete mixes. This is particularly important in coastal areas facing sand scarcity due to urban expansion. Mancini et al. 2024 highlight how using tailings as aggregates can help address the demand for disaster resilient infrastructure. Additionally, processed tailings can be used as soil amendments in agricultural applications. In mining intensive regions like Benguet, these tailings can rehabilitate degraded lands, fostering agricultural productivity. Lastly, forming partnerships with local industries could unlock further value. For example, cement manufacturers in Bulacan and ceramic producers in Batangas could reuse tailings in their production processes, creating economic benefits while reducing environmental impact. The second key focus area is waste minimization through innovative technologies. Bioremediation offers a nature based solution to address contaminants in mine tailings. For instance, the Teres vitata fern, native to Southeast Asia, has been proven effective in absorbing arsenic, a common contaminant in mining operations. This method is particularly suited to tropical ecosystems like ours, as noted by Tayebi Korami et al. Of 2019. Another innovation is rainwater harvesting. By integrating rainwater collection systems into plant operations, treatment facilities can address water scarcity, especially in regions like Mindanao, where industry water supply is affected by seasonal variability. Finally, waste recovery is an essential strategy. Capturing heat from processing equipment can significantly reduce energy costs and carbon emissions. This is particularly relevant in the Philippines, where reducing energy reliance is a national priority. The third focus area is resilience to natural disasters. Given in the Philippines' vulnerability to typhoons and earthquakes, treatment plants must incorporate disaster resilience design. For flood prone areas like Palawan, elevated tailings dams with reinforced barriers can prevent failures during heavy rains. In seismically active regions like Davao, treatment plants should adhere to the National Structural Code of the Philippines, or NSCP, to ensure structural integrity during earthquakes. Additionally, implementing real time monitoring systems is crucial. By leveraging IoT technology, facilities can track environmental data and ensure compliance with government regulations, such as those set by the Department of Environment and Natural Resources, or DENR. These systems can enhance safety and operational efficiency.
Now, for other suggestions in improving the sustainability of our treatment plant, we can incorporate renewable energy and community integration. So, renewable energy source is the installation of solar and micro hydro systems that can power facilities in remote areas. So, through this, we can reduce carbon emissions as well as address the energy needs of the treatment plant. Next, we can also foster community engagement by initiating common community led recycling programs that can create livelihood opportunities in mining regions like Cebu, and also education campaigns, which can foster understanding of sustainable mining's benefits, can increase community acceptance towards the treatment plant. Also, we can incorporate process monitoring and data analytics by installing IoT sensors and AI to effectively monitor contamination risks and effectively optimize each process step of the treatment plant by identifying risks and possible contaminations and maximizing efficiency. And recent advancements from DOCP shared highlight this technology, such as the cloud-based data integration and visualization of sensor output made from Ateneo de Manila University, which can prove to be useful in such applications. We can also incorporate predictive modeling, which utilize machine learning to analyze contamination patterns based on sampling and historical data, and thereby optimizing sampling and recovery process. Lastly, we can also consider the environmental impact mitigation by incorporating low impact reagents, specifically in our flotation process, which commonly use dangerous chemicals. So, if we are to replace these chemicals by low cost, non toxic, and biodegradable reagents, then therefore we can easily integrate it into the existing treatment plant. So, examples of these are modified fatty acids and oils, plant based frothers, bioreagents, and activated carbon additives. Lastly, by practicing transparency and health impact assessment, we can facilitate open and transparent communication with the local communities to provide additional monitoring of environmental impacts, as well as conduct regular health impact assessment to effectively identify possible health risks regarding or surrounding the treatment plant.